Hello everyone, I'm Jose Carlos from Cuba. I'm PhD student in Tarragona, in Spain. I will present my last research titled Flexible Sensor Utilizing Polypyrrole Laser-Induced Graphene Nanocomposite for Room Temperature Ammonia Detection. Let's start. The ammonia is the colored gas that exists in different concentrations in the atmosphere. The ammonia measuring is important in different applications, like air quality monitoring, regulation of the agricultural and livestock, safety insurance in the chemical industry, and the wastewater monitoring. For this reason, in recent years, many approaches have developed for ammonia gas sensor. For example, optical, electrochemical, and chemoresistors. Optical and electrochemical normally is very expensive and hard to miniaturize. For this reason, the chemoresistance is the good alternative for measuring gas sensor. The chemoresistant materials change your resistance to change different environment chemical. The metals, for example, the more common chemoresistant materials is metal oxides, transition metal decalcogenes, and graphene. In the case of the graphene is in the last year is have many interests due to their unique properties, in special for high sensitivity to change in gas concentration, potential for selective detection through chemical modification, and ability to work and room temperature, making them a good candidate for weather gas sensor. However, the graphene synthesis method have drawbacks related to the high cost, mass production, and incorporating graphene into flexible electronics. So, in 2040, Professor Tour present one approach for make a high porous graphene from the commercial polyamide with use CO2 laser. The laser-induced graphene have excellent electric conductivity, high porosity, and good mechanical flexibility. For these characteristics, this material is good alternative for gas sensor. For example, this study with the same authors present the first gas sensor using laser-induced graphene. In the other study, the author present the moisture-resistant and stretchable gas sensor for NOx, and we can see the good response for this application. We can see the response for the other gas is very low. For this reason, it's necessary make modifications to the LIG for improve the selectivity to the other gases, different to NOx. For example, in this paper, using LIG nanocomposites for different materials or metal oxides and transition metal decalcogenes. we can see it respond to different gas and increase the selectivity for these different gas. Okay. In our group, MINOS, we have a long history developing gas sensor. One of the research, Juan Casanova, is here. Development and graphene commercial nanocomposite for polypyrrole for improve the selectivity of the ammonia gas sensor. He put the nanocomposite in the commercial aluminum substrate with platinum electrodes, and we can see he respond to the different concentration of the ammonia. Okay, according for the points I mentioned in the introduction and the resource obtained for research, we decide using LIG gas sensor instead of graphene commercial graphene and platinum electrodes. We use commercial polyamide for LIG synthesis using CO2 laser with these parameters. Okay. The sensor have one sensing area and two pads for connecting to the measuring system. To improve this connection, we silvering was broadcasted in this area. At the end, we have a commercial we have a graphene layer for graphene layer providers wall area sensing area electrode connection and electrode all together. We have this approach is very cheap. We can have one sensors, maybe 10 sensors, less than €1. Is very cheap. Okay. We can see the Raman spectrum of the LIG. This is the characteristics pictures of the graphene is demonstrated. The graphene is 6 in the LIG. This is the microscope electro image. You can see the 3D porous morphology. This is used for morphology for the gas sensing application. Okay. In the next step, we make polypyrrole layer by electropolymerization in bare LIG electrode. For this, we prepare pyrrole solution with electrolyte and organic dissolvent. Okay. For the synthesis, we are using common potentiometry method with current of the 50 microampere millimeter for square for 10 minutes. We can see this is classical electrode deposition. We using the bare LIG as working electrode. Okay. This is the dynamic response of the bare sensor to polypyrrole and LIG nanocomposite for to exposure to ammonia gas. We can see the resistance is increased. Is a result of the interaction of the p-type materials, LIG, and the reducing gas, the ammonia. This plot is demonstrate the nanocomposite improve the response, the repeatability, and the stability of the baseline. Okay, this is the calibration curve of the buff sensor. The response is 20 times more high, and the considering the slope of the curve, we can see we have 40 times more sensitivity to the polypyrrole LIG nanocomposite than the LIG bare sensor. Okay, for conclusion, we are developing a flexible gas sensor for ammonia detection operating in room temperature, high cost effective method, and have sensing performance improved by electrochemical growth of the polypyrrole. And also explore various electrochemical deposition methods to achieve different morphology of the polypyrrole, optimize sensor response to ammonia for commercial use, and checking the real performance of the sensor in lift stop far for load time.
Thank you so much for your presentation.